So, now we go to the second part of hydrodynamic description. So, vorticity. Okay. So, I am going to describe what is vorticity and the evolution equation for vorticity, okay, and why it is important. So, this is an example of this big hurricane Irma which came last year, I think, okay, in US. So, this is a vortex hurricane, big hurricane, and it is going, it is going like this. In northern hemisphere it will be anti-clockwise, okay, swirling in. Now, of course, we can work with velocity field, but it is also a good idea to construct some more variables which are useful to which are useful variables like energy. So, given velocity field I can also construct energy u squared. Another quantity is vorticity. So, vorticity is just curl of u, and curl if it is non-zero then it gives you some kind of curliness, like magnetic field, curl of B is current. So, we say curl is a useful quantity which gives you, is there a current, then I can say I can get a magnetic field, or divergence. So, these are very useful constructs for vector quantities. So, curl of u, you will see that is a very useful quantity, is a vorticity, and typically this is non-zero. We also have curl free situation, but typically in turbulence we will find the curl is non-zero. Okay. So, this is what I will describe, what is the equation for omega. So, this in some sense this is what vector calculus people say, that it gives you curliness. So, this is curly, this is going around, curly is curliness. Of course, we need to compute, so this curliness of velocity field will be different than curliness of magnetic field. So, you have to compute, then only we will know. Okay, I want to make a caution. So, if I have some just velocity going like this, does that mean it has a non-zero curl? Example where it is going down like this, but it has zero curl except in the center. Now, you know the example, no? Everybody knows the example. What is the example where things are going around like this? What kind of vector field gives you zero curl everywhere except in the center? So, curl of B, now just go back to your electrodynamics, curl of B is J. I am not putting mu naught J, okay, let us put mu naught J. So, if there is a current source here at the center only, line current, then B, curl B will be 0 everywhere except in the center. The source is in the center, no, there is a delta function. For that particular case, delta of R at the center. Now, so what is the B? Now, this has been solved, no, you would have solved it. B is tangential and it goes as 1 over R. So, if my B field, I am writing it here, is 1 over R E phi. So, you can compute curl for this vector and curl is 0 except in the center where it is a delta function. So, something curling around does not mean it has a non-zero curl. Okay, so, but I can change the function to, let us say, R instead of 1 by R, then it is non-zero curl at everywhere. Okay. So, I just caution, but if something is curling around, it is a good idea to check curl, it may be non-zero most of the time.
Doesn't rigid body rotation come under the same effect?
Rigid body rotation has, okay, so what is the rigid body rotation, what is omega for rigid body rotation?
Rankine vortex.
No, it is a constant omega for all R, okay. So, it is, this will be constant C phi, right. Velocity field will, no R, velocity field will be R times, so let me erase this. So, I should put this 1 by R. Rigid body rotation, what is let us put it here, rigid body rotation. Omega is constant.
That omega is angular speed, it is not the vorticity, this is not the...
No, so let us put omega, capital omega. So, velocity field at any position will be omega times R, okay, omega R, and it is E phi, I am assuming that there is only one axis rotation. Now, this one will have non-zero curl, Okay. So, this is just the kinematics. Yeah, this omega is not same as curl of omega. So, what Supratik is right, this omega is the rotation of the rigid body. So, you can take a disk is rotating. Okay. Okay. So, anyway, these are useful way to look at the vector fields and connections like this. Vorticity is, I will tell you, very strong connection with electrodynamics, and we can do lot of interesting analogies. I will mention it in couple of minutes. So, we start again with whatever we just learnt, Navier-Stokes equation. Okay. So, this same equation which we just did, I dropped primes and I do not want to keep primes. So, this one identity, now this is a useful identity which we can, is there in my notes which I will give you. So, this nonlinear term can be written as in terms of what is omega and this one and this. Okay. So, if you substitute, what will I get? I just substitute, replace this term by these. So, it is quite easy to see. I am just going to click the next slide. So, u cross omega in the left, minus u cross omega, it goes to the right, it comes with a plus sign. Correct? I agree, right? This was negative in the left, so it comes. Now, this is a gradient of u squared by 2, which is a plus sign, so it goes to the right. So, anyway, this is just straightforward. Okay. So, this term is this one, and u cross omega is this. So, this is straight from Navier-Stokes equation. Now, I can take curl of this, I take curl of this equation, I want vorticity, no. So, curl of this equation. So, d by dt and curl commute, commute means I can change the order. So, this will become dt by omega vorticity. And what about curl of a gradient? 0. So, curl of a gradient is 0. So, pressure is gone. That is a huge advantage in vorticity formalism, pressure disappears, and now this other term will be curl of u cross omega, and then we get curl of. So, in fact, I have this equation, the next line is here. Okay. So, let us erase this part. So, pressure disappears and we get pressure and u squared both disappear. So, we get this term, and this is curl of Fu. So, this object, this is curl of Fu vector. Okay. Now, by the way, this notation bold means vector. So, when I say bold, this means vector, I am not putting arrow, but this is a vector, this is a standard notation. Okay. Now, curl and Laplacian also commute. So, that means this will become curl of u as is omega. So, this is equation for vorticity, and this we will use it in future. Okay. So, we can also time step it, but it is also tricky. So, if you can't simply time step omega because you need u. So, if you are, well, I will not discuss it here, but it is not that omega replaces u completely and you can just work with omega, you need to compute u. In fact, that will require again Poisson equation. Okay. So, I will not delve into it, but this equation which is for omega. Now, some people who know MHD, magnetohydrodynamics, I just want to make a remark that omega has very similar structure as magnetic field. Okay. So, in fact, it has exactly same structure. So, d by dt of B MHD. Okay. So, let me just write magnetohydrodynamics, which we will do it later. It is written as curl of u cross B. I will put force as 0, okay, and nu grad square B. This equation for magnetic field under MHD approximation. So, omega and B, you can see this analogy, except the analogy is not one to one analogy. I also want to caution you, in fact, Bachelor, which is a very big shot, he made this analogy and he made some deductions, and they are incorrect. Okay. So, this is not fully correct. The reason why this is not exactly one to one, so omega is curl of u, but B is not, B is independent variable, but omega is a dependent variable. Okay. So, it is useful analogy, and I will show you that B and omega have very similar dynamics as well, but you can't simply derive everything from equation for omega. So, we will discuss that in this course.
But cannot the vector potential of B be interesting then?
Yes, yes, we will do that later. That will be also tricky, yeah. But omega and B are related. I'm going to show you in the next slide itself some connection.
Will the mu in the second equation be the same as kinematic viscosity?
Yes, yes, it is same, because this curl acts on this.
MST equation.
No, that is diffusion. Oh, sorry, you are right. Thank you. So this is eta, magnetic diffusivity, but it's a diffusion term. It's similar form, but it's not same nu. Okay, it's a different parameter. Okay, next one. So we can also simplify this equation. Another form of this equation. So I will use another identity. So there are a lot of vector identities, which I don't remember myself, but we'll so curl of A cross B. Now this is interesting way to remember. So what is A cross B cross C? So this I like C cross A cross B. So the A C dot B. So A has come here and C dot B. So C is curl. So it is C dot B. So it is divergence B plus B dot divergence. So because you have to do twice. So divergence is acts on variables. Okay. So this is how you can remember if you like, but that's aside. And this is our identity which we need. Now U is A and B is omega. Right, from here I want to replace this one. So what is del dot U? 0. So this one is 0. Del dot B, this del dot omega is 0. Divergence of a curl is 0. This is 0. So we get two terms. So U dot grad omega, and this is B is omega. Sorry. So I erase this one. The omega dot grad U, and this is U dot grad omega. So replace these two terms here. So what we get is this. So this one is negative, which comes to the left, which is positive, this one, and so these two terms are sitting here, this one and that one, and this is usual before as before. Okay. So this is another form for omega dynamics. So this is the total partial T plus U dot grad omega, as I said, is total derivative or convective derivative, material derivative. So the d omega dt is equal to this. Now this again is MHD equation, same equation as B, except of course as Roshan pointed out, I have this. I dropped f omega. If you like f omega, you can keep here. Okay. Okay. So this is in 3D. I want to make this remark. Okay. So this term is advecting the vorticity. No, it's like advecting. So in fact, it's same as advecting temperature. It carries the temperature, or also the vorticity is a vector. So it advects the vorticity. But this term, what does this term mean? This term is stretching the vorticity, okay, which will show stretching. So this is the interpretation. So you take this vorticity field, the velocity field will stretch this. So vorticity can decrease or increase because of stretching. Exactly same analogy which is made for MHD. Magnetic field term, magnetic field will change because of velocity field will. So if the velocity field at two ends are different, and there is a tube or vorticity tube, so this velocity here, velocity here, so it will stretch. Okay. So this is the interpretation of term. This term is called stretching of vorticity. And in 3D, of course, this is non-zero. In 2D, I will show you that is 0. Okay. So this is like one-to-one analogy of vorticity and magnetic field. Okay. So in 2D, so let us just also talk about 2D, which is also very useful. So 2D means there is no z component. So my notation will be the motion is only in x y. So you can just think of a fluid motion on this surface of the this floor surface. 2D means there is no z component. So my notation will be the motion is only in x y. So you can just think of a fluid motion on this surface of the this floor surface. So you can just think of a fluid motion on this surface of the this floor surface. 2D means there is no z component. So my notation will be the motion is only in x y. real example is soap film. So, people do experiments. In fact, in IIT there is a nice experiment. So, there this Sanjay, he is in aeronautical department, he does experiments on soap films, you know. So, these experiments is 2D. So, there is no Z component, it is basically 2D. Now, what is vorticity of this? I can compute vorticity easily. So, omega, let us do it, because this is important, so I want to do it once. So, x, y, z, dx, dy, dz, ux, uy and 0. So, what happens to x component? So, by the ux and uy only is function of x and y, not function of z. So, what happens to x component? This minus this. So, partial z uy is 0, no, because uy is not a function of z. So, x component is 0, 0. What about y component? Partial z ux minus partial x 0, 0 y component. What about z component? It is partial x, I am going to write here, uy minus partial y ux. It is non-zero, but omega has component only along z direction. So, this is what I got in my next equation. So, this is omega, I can call it scalar, yeah. So, this is somewhat, so this is a vector and this is scalar, or I may call it omega z if you like. It is only one component. So, my velocity fields are in this plane, you know, things may be going like this, or it could be, you know, the various motion, but my vorticity field is only along z cap, vertical direction. So, what happens to omega dot grad u term? 0, because omega is along z and grad is only active along x and y. So, it is naturally 0. So, in the previous slide, the right, so there are two terms, one is u dot grad omega, other is omega dot grad u. Omega dot grad u term is 0. So, what we get is this. I put force to be 0, so force is on. So, d omega by dt is here. It is, which will be dissipated by viscous term. It has no source, stretching is 0 for 2D. So, in some sense you see that these vortex tubes are infinite, they do not change with z. So, and there is no velocity in z direction, so nothing to stretch it. It has no vorticity is not along. So, this horizontal guys can't do anything. It can only advect this pen, you know, this vorticity. So, vorticity does not local material derivative of omega is 0 if viscosity is 0. Okay. So, I must say what fluid can do, it can only kill the vorticity by dissipation, it cannot increase it, it cannot change it other than viscosity. So, this is what happens in with vorticity. So, this is what I wanted to communicate for vorticity. Thank you.